I'm on a spaceship and I'm going at half the speed of light, and I turn on a flashlight, how fast is the light coming out of that flashlight? It's going at the speed of light. If I'm going on that spaceship at half the speed of light past my friend on the Earth, and I turn on the flashlight, how fast do they measure that light to be? Well, they measure it moving at the speed of light. You might think, hold on a second, shouldn't I add the speed of light plus half the speed of light to get 1.5 times the speed of light? And that would be true if you were talking about sound waves or any other kind of wave has that property. But light waves just don't. Light waves always travel at the speed of light no matter what. And it has all sorts of important consequences, like it changes the way the time flows. It means that people can disagree about the order of events that things happen. Like, we could be watching a race where like a rabbit is running against a turtle, and you could say, oh, the turtle won. And I could say, nope, the rabbit won. And we could both be honest about it, and we could both be correct, and we could disagree, because the order of events of things happening is no longer universal. Every place in the universe has its own clock, and there's no like set order to events in the universe. And that comes directly from this observation that light always travels at the speed of light no matter what, because it sort of unlinks all the observers in the universe. It says that your story doesn't really have to be consistent with Bob's story or with Sally's story over there. Everybody has their own story, and they can disagree and all be correct. It's kind of bonkers.
So is it like watching the movie Interstellar?
Yeah, Interstellar has a lot of these effects. Those effects are more gravitational time dilation, which is also super fascinating. Interstellar tells you or illustrates the principle that when you are near something very massive, that your clock slows down. So, for example, if you go near a black hole, somebody far, far away, looking at your a clock you're holding through a telescope, they will see your clock ticking more slowly. So every time their clock says an hour has passed, your clock will say a second has passed. And the other direction, if you're near the black hole and you're using a telescope to look at somebody else far away holding their clock, you'll agree. You'll say, yeah, my clock is ticking slow, and the rest of the universe is like zooming forward into the future, right? Because you'll be running slow and they'll be running fast. And that's pretty cool, but the amazing thing is that there you agree, right? You both agree on whose clock is running slower. In the case of moving really quickly, then there's disagreement. Like, if I have a clock and you have a clock and you get on a spaceship and you're leaving Earth at 90% of the speed of light, if I look at your clock, the rule is moving clocks run slow. If I look at your clock, then I see your clock is running slow. If you get your telescope out and you look back at Earth at me, you say, no, you're moving. I'm in my spaceship. You're moving 90% of the speed of light the other direction. Your clock is slow. So in that case, we both think the other person's clock is running slow. It's like, well, what you might be tempted to ask, what's actually happening, right? Which is right. They're both correct. They disagree, but they're both correct. And so that's the kind of symmetric time dilation that comes from relative velocity. That's really confusing, because we have this sense that physics is teaching us what's really out there in the universe. It's helping us figure out the story of the universe. But now we have to understand that there isn't a story of the universe. There's an infinite number of stories of the universe, and they don't all have to agree. And the story you tell depends on where you are and how fast you are going. So it's not just like a relativity of time, it's like a relativity of truth. It's like a relativity of history. It really teaches you that what we've learned about the universe and all of our intuition from walking around very slowly with large objects like us is not representative. It's just an example. It's an extreme case of the universe and not something we can generalize. And it's a lesson that the things we think are true of the universe might not be, that we might be making assumptions or only studying a test case. It's like scientists who have only been studying the tail of an elephant, not even realizing that there's more out there, and thinking that the whole universe is just made out of tails. And now we realize, oops, turns out there's a bigger story.
Yeah, and speaking of light travel, is there hypothetical conditions where we can travel faster than light?
So it depends a little bit on the legalistic interpretation here. If you want to move through space, you cannot move through space faster than light. Only things that have no mass, like photons, can travel at the speed of light, and things that have any mass can never travel at the speed of light. And nothing, even photons, can move faster than the speed of light. However, that depends on what exactly you want to do. If, for example, you want to get from here to Alpha Centauri, which is about 4 light years away, and you want to do that in less than 4 years, that's how long it would take light to get there, that might be possible. It's not possible by moving through space as faster than the speed of light, but you can play with some loopholes. The rule is you can't move through space faster than light. The rule isn't, hey, let's change the shape of space. Because we've discovered in the last 100 years or so that space is not just like the background of the universe, the stage on which everything happens. It's actually something dynamical. Like mass tells space how to bend, and space tells mass how to move. And we talked earlier about space expanding, right? Well, we know that space can bend and ripple and expand and do all these things. And that we can even be strangely connected. Like one point in space might be connected to another point in space which is otherwise far away.
And one last question from me is actually from my friend who unfortunately isn't here today, but does the edge of the universe run at the same time as the rest of the universe?
So what do we mean by the edge of the universe? There's a couple different ideas there. One is the edge of the observable universe. So we can't see the whole universe because the universe is not infinitely old, like 14 billion years old, which means we can only see things where light has had time to get here during the existence of the universe. Things that are more than 14 billion light years away, in principle, we can't see them because the photons are still on transit, or they haven't gotten here yet. Now, that's not exactly true because the universe is expanding, so we actually can't see things that are now more than 14 billion light years away because they used to be closer and their photons can get here. But anyway, there is an edge to the observable universe because of the non-infinite speed of light. So that observable universe is expanding. Every year it expands by a light year per year because now there's more time for stuff to get here. And so it's possible for photons to arrive, for things out there in the universe we've never seen to be illuminated, for their photons to get to our eyeballs and say, oh, I see that galaxy now. So that is expanding at 1 light year per year. Or maybe your friend is asking about the actual edge of the universe. One thing that's really fascinating is that we don't know the shape of the universe. Not only do we not know its full size, the observable universe is a portion of the universe. We don't know what's past it. We don't know if it goes on forever or if there is some edge to it. Perhaps the universe is closed the way like the surface of a sphere is. And if you keep going one direction, you come back to where you started, in which case the universe sort of has no edge. It's also possible that the universe, that space itself, is finite and does have some edge, some like weird boundary beyond which there's just like no more space. We don't know. We have no idea if that's true or why that would be true, and you know how space and time would operate in that scenario. We just really don't have any idea.
Got it. Thank you. Actually, I'll hand it to Thomas for the next question.
So, to continue on the topic of the expansion of the universe, how does our current understanding of the expansion of the universe fit with our understanding of the on the conservation of matter, of energy?
Yeah, great question. Wow. So we used to think that matter was conserved. If you watch a chemical reaction, you get the same amount of stuff out as you got in. Right? We used to think that was true. Now we know it's not true. Matter is just not conserved in our universe. It's not a fundamental principle. You can turn energy into matter and matter back into energy. And it's important to think about what that means, right? It means that matter is not like essential. It's something that arises in the universe, but it's not a basic component. It's like if I asked you, do you expect there to be a constant number of ice cream cones in the universe at any given time? Of course not, right? Somebody makes an ice cream cone, somebody else eats an ice cream cone. It goes up and down. There were billions of years in which there was no ice cream in the universe. It's not like an important fundamental quantity. Nobody should like billions of ice cream cones. Well, matter turns out is like that, right? It's not fundamental. And so then we thought, well, what about matter and energy? Like just energy, all energy combined, including kinds of matter. People thought certainly energy is conserved, right? Yeah, wrong. Turns out energy is not actually conserved. Energy would be conserved if space was fixed. So if you live in a universe where space is not changing, then energy is conserved. There's this really deep principle in physics called Noether's theorem from Emmy Noether, a famous mathematician from about 100 years ago. She discovered that every time you have a conservation law, or conservation of energy or conservation of momentum, that comes from some sort of symmetry of the universe. That's why we have these conservation laws. So for example, conservation of momentum, why do we have it? We have it because there's no special location in the universe. If you do an experiment here and you move it over a meter, you should get the same answer. There's no special place in the universe. And what that means technically, if you're physics students, is you could take your Lagrangian and you can shift your coordinate by a constant. It doesn't change the equations of motion, right? Because you're taking a derivative anyway, that constant disappears. That's why you have conservation of momentum. Conservation of energy comes from the time constancy of the universe. It says if space is always the same, then energy is conserved. But space is not always the same. In our universe, as you said, space is expanding. We are creating new stuff, new space all the time. The space between here and another galaxy, there's more of it now than there when we started this conversation. What that means is there's more energy in the universe because every chunk of space comes with dark energy. Dark energy is the phrase we use to explain this accelerating expansion of the universe, not something we understand, just like a fancy name to describe our lack of understanding. But something we're pretty sure about is that it doesn't get diluted. Like if you take a universe with two bits of matter and you expand it, now you have a lower matter density because the matter doesn't change and there's more space. But dark energy, we think, comes along with the space. Every time you create a new chunk of space, it comes with dark energy. So the dark energy density is constant, which means as you add more space, you're just creating energy. And the first natural question is, well, where does that energy come from? And you ask that question because you imagine energy has to come from somewhere. But if I asked you, like, you had an ice cream yesterday, where did that ice cream come from? You said, well, somebody created it. They took the constituents and they made it. Like, because you can just create ice cream. Well, you can also just create energy. The universe does it. We don't know how. I can't create energy or space, but the universe somehow knows how to knit together new bits of space. And that violates the conservation of energy, which tells us energy is like ice cream. It's not fundamental. It's close. It's interesting, but it's not fundamental.
That's really interesting. Maybe you've touched on this a little bit on dark matter. We often hear about dark matter, like when we look at space news and everything, but sometimes I feel like it's misunderstood because like we often talk about matter, but dark matter, like sometimes it seems weird. So what exactly is dark matter?
I wish I knew. Dark matter, we don't know what it's made out of. We do know that there is more gravity in the universe than we can explain. Like if you look out at galaxies, they're spinning. And we ask, is there enough gravity to hold these galaxies together? Because think about what happens on a merry-go-round with you and a bunch of ping pong balls. Put the ping pong balls in the merry-go-round, spin it. What happens is they fly off, right? Unless there's something holding them on. And so in the case of a galaxy, it's gravity holding the stars in the galaxy. But if you just add up all of the stuff in the galaxy, there's not enough visible stuff out there that has gravity to hold it together. So we think there must be something else in there. So dark matter is really just an explanation for the missing gravity. And we see it in lots of ways. Like we also see it in the very, very early universe. We see these photons from the very beginning of the universe called the cosmic microwave background photons, when the universe was cooling down and it went from opaque, like the sun, like the center of the sun, and it cooled down and finally became transparent like most of space. And at that moment, a bunch of photons, which had just been created, suddenly could fly free through the universe. And they're still around. And we can use those photons to see a picture of the very early universe. And we see in that picture wiggles in those photons that can only be explained by the presence of dark matter. And we know that the universe, the structure of the universe, like the way galaxies have come together, without dark matter, we wouldn't have galaxies in our universe. There isn't enough gravity to pull stars together and galaxies together without dark matter. So what is dark matter? It's the fact that there is more gravity out there than we can explain. And if there's some sort of like new kind of particle, right? Not quarks, not electrons, not anything that we know, some new kind of particle that doesn't feel those forces, but does feel gravity out there floating in the universe, that would explain all of it. We haven't seen this particle. We haven't like identified it and said, oh, here's one. We saw it do something. And it's tricky because we think that dark matter only feels gravity. But gravity is the weakest force. By like 10 to the 36, it's weaker than even the weak force, which means it's very hard to do experiments where you have like one dark matter particle and you measure its gravitational effect because it's basically zero. So you can only do the dark matter experiments on like the cosmological scale, like galaxy size or maybe a little smaller, which makes it very challenging. So we don't know what dark matter is. We know that there's something else out there. Like it's definitely there. Something is there. Is it a particle? We don't know. Is it some other new kind of matter we've never seen before? I hope so. It could be primordial black holes created in the very early universe. It could be something else even weirder that we haven't even thought about yet. The important thing to understand is that there's more dark matter than there is our kind of matter. What we consider normal matter that makes it me and you and hamsters, that's 5% of the energy in the universe. Dark matter is 25%. So it's very dangerous to say, oh, I understand our matter. Let me extrapolate and say the dark matter should also be like that. It's just like thinking the rest of the elephant is made out of tails, right? I've studied the tail for 100 years. Maybe the rest of the elephant is like a linear combination of tails or something. That's ridiculous. And so it could be that it's something beyond our imagination, beyond our current understanding. But it's definitely there, creates gravity, very likely some kind of matter. We just don't know what it's made out of yet.
So we know how much dark matter there is in the universe then. So like how much of dark matter is there and how did scientists like measured how much dark matter is there?
So we think that there's 5 times as much dark matter in the universe as there is normal matter. It means for every kilogram of stuff, there's 5 kilograms of dark matter. And that dark matter is not just like out there in space. It's here with us, right? It's all over the place. The volume of the Earth has dark matter in it. There's dark matter in this room with you. It's more spread out than normal matter. It doesn't clump together the way normal matter does into like planets and galaxies and squirrels and stuff. It's like a big fluffy cloud. So it's actually less dense than normal matter is in an arbitrary unit of space. So on average, there's more of it. It's just that our kind of matter gets very, very dense and forms planets. So we know how much dark matter there is because we see its gravity, right? We see its effect on galaxies. This is how much stuff you would need to keep a galaxy together if it's spinning this fast. Without dark matter, it would just blow itself apart. In the same way, we need that much dark matter to form the structure of the universe. Without that much dark matter to create gravity and pull together things in the very beginning of the universe, remember that in the very early universe, it was just basically a huge cloud of hydrogen gas, evenly spread out. How does that form stars? Well, you need like one little spot to be a tiny little bit more than any other spot. And then that, because it's more dense, it has more gravity. And then gravity pulls and pulls and pulls. And as it gets more dense, it gets stronger and eventually becomes a star. That takes a very, very long time if you have a big cloud of hydrogen. It's much more helpful if you also have a huge clump of dark matter hanging out right there, adding its gravitational force to the formation of these stars. And so without dark matter, without saying, well, we need 5 times as much as normal matter, you just don't get stars and galaxies forming in our universe. So because we can see its gravitational effects, we can tell how much dark matter there is. Though, again, we still don't know what it is exactly.
Since dark matter has been unobservable by humans, could it be possible that there is a species of animals or something in the universe that could be more adept than humans to sense dark matter?
It's certainly possible that dark matter does interact with our kind of matter in some way that we haven't figured out yet. And it's possible that aliens out there have a sense that can observe that kind of new force. So it's certainly possible that some sort of alien physicist sees dark matter with their eyeballs. Remember that most of the universe is invisible to us. Even the parts that we do understand, even the standard model, most of those particles are invisible to us. Like in the room with you right now are billions and billions of neutrinos raining down on you. You just don't see them. If you could see them, you could hardly see anything else because the universe would be filled with them. If you somehow had receptors that could see the weak force, the way your eyeballs can see electromagnetism, if you had weak force eyeballs, you could see those. So the lesson there is that the universe is dark, is mostly invisible to us. That what you see, your imagination of what's out there outside your brain, is a tiny fraction of what's actually there. It's not a representative sample. So yeah, absolutely. Alien physicists or alien beings might have some new sense which is capable of detecting dark matter and sort of visually seeing it. That would be pretty awesome. I hope so, and I hope that one day they come here to Earth and explain to us what dark matter is. I look forward to that.
Mm-hmm. Yeah, and it would be, I don't know if it would be possible, but it just popped in my head that it would be interesting to find some aliens that are able to see dark matter, but that aren't able to see the matter that we see. So it would create like an exchange of knowledge.
And it's tempting also to wonder if there are aliens made of dark matter, right? Maybe because there's so much of it out there, maybe it does something interesting. So far, we think that dark matter probably isn't capable of the complex interactions that our matter is, right? Like we can make chemistry and biology and economics and stuff because we are capable of clumping together, forming these dense objects that have complicated interactions. Dark matter, we don't think has really complicated interactions with itself. We think it just sort of passes right through itself. But we're really just not sure. And there's so much dark matter that it's possible that like most of it doesn't have complicated interactions, but maybe a little tiny version of it does.
Assuming that one day we could track all the dark matter, all the dark energy in the universe, would the universe still appear to be expanding infinitely, or would we return to the previous theories where the universe will stop expanding at some point?
Yeah, the problem is that we don't know how to predict the future because we don't understand dark energy at all. Like, don't think about dark energy as here's something in physics we can talk about and make predictions of. It's more like a summary of our observations. We've noticed the universe is expanding and that expansion is accelerating. We don't have any explanation for why that is. We talked earlier about like maybe it's this potential energy field, but that's 10 to the 100. Those calculations are off by 10 to the 100. So the truth is that dark energy could change. It could be accelerating the expansion of the universe today, and then tomorrow it could turn around and cause a big crunch. It could wait 1 billion years. Like, the universe, dark energy only turned on about 5 billion years ago. maybe it's going to turn off. Maybe it's going to turn around. Maybe it's going to jump up and accelerate even more quickly. Nobody can predict the future because nobody understands the mechanism. It's like we're driving in a car and we have no idea who's driving and what their goals are. So you have no idea where you're going to end up.
Perfect. Then we'll finish off with one quick, I guess, pop culture question. So are you excited by the current state of the space exploration or space race?
Absolutely. I think it's very exciting, the sort of new eyeballs we're building in space. We just built the James Webb Space Telescope, and we have a bunch of missions planned to go to Europa and to sample the oceans there and to go to Venus. I'm very excited by the sort of robotic exploration of the solar system and space telescopes. I think that's scientifically very, very exciting. There's another program of crewed exploration of space, like sending people into space. And I think that's exciting for astronauts and for people who want to be in space, like adventurers. Scientifically, it's not that exciting. Like, you don't really learn that much by putting people on the moon. Costs billions of dollars and maybe lets you fight with the Russians in another place rather than on Earth. But you can't really do much more science by having astronauts on the moon than you could just by sending robots, which is a lot cheaper and less dangerous.
But are you excited by the prospect of going to Mars?
I do not want to go to Mars. Anybody who thinks about going to Mars should first take a trip to Antarctica, which is much more pleasant than Mars. And so if you think a vacation in Antarctica is exciting, then maybe you should think about going to Mars. Mars sounds like a terrible, terrible place to live. And so I'm not excited about going to Mars at all. If people want to move to Mars, more power to them. I think we should think carefully about colonizing space. We didn't think carefully about colonizing the Earth. We made a lot of terrible mistakes and horrible genocide and destroyed a lot of valuable knowledge. And I think before we, send our corporate raiders off to Mars, we should think carefully about what damage they might do when they get there, and if we really want them representing humanity.
Thank you so much for taking this 1 hour with us. It has been wonderful. Thomas, any last words?
No, I think we've talked about everything. Well, thank you so much. Or maybe, where can we find you on the internet? Because you wrote many books in the last few years.
Sure. Thanks very much for inviting me. It's been a pleasure. I love talking about this kind of stuff. Everybody is curious about the universe. I'm regularly heard on our podcast, Daniel and Jorge Explain the Universe, that you can find everywhere you get podcasts. And I wrote a couple books. One is called We Have No Idea, about all the mysteries of the universe. And another one is called Frequently Asked Questions About the Universe, that features answers to many of the questions we talked about today. All those projects are together with my friend Jorge Chan, who also provides hilarious and fun illustrations for those books.